denominator anymore. And after you cancel out, you can plug in the 0. And technically it's not going to be equal to 0, but for all practical purposes, h is going to approach 0. So let's just kind of see what happens now. Oh, well, if it approaches 0, then this should approach. When h approaches 0, the rate of change approaches 6 feet per second. The average rate of change approaches the instantaneous rate of change when this increment gets smaller and smaller. And that average rate of change approaches 6 feet per second. That's what the instantaneous rate of change is going to approach. Does that make sense, you guys? Anna, how are we feeling with this? Are we? Okay. So that's a big idea. And again, all derivatives are based off of this change in y over change in x. It's based off of this average rate of change for really, really small increments. When you get really small increments, that average rate of change becomes sort of an instantaneous rate of change. Okay? So I'm going to talk about this briefly, and then never talk about it again for the rest of the year. And when you get into grad school, you can fight about this definition and work on it more then. This is the formal definition of a limit, which came in this century, or in the 1900s, way past all the good stuff going on with Newton and Leibniz. But here's what a limit is, the formal, and I'm going to read it and then end it there and talk about what we want from it. Let C and L be real numbers. The function f has a limit L as x approaches C if, given any positive number epsilon, there is a positive number delta, such that for all x, the absolute value of the difference between x and c is between 0 and delta. Then the absolute value of the difference between the function value and L is less than epsilon. Yes. What that means, and look at my note for what that means, and this one doesn't even help that much. Roughly what it means is, if you can bucket all of the values between your x value and some specific number, that means you can bucket all the y values. And as all of these values are going towards some c, all of these y values are going towards some L. And let me show you. I'm going to show you what. Yes. It is confusing. Let me show you some practical examples. Okay. And this is what we're going to be dealing with, because this is it's not an A/B topic, so I'm not really going to deal with it. It's a hot mess. Here's what we need to know. This notation, which in Math 4 we dealt with a ton. The limit, as x approaches some number of some function, approaches some number. The limit, as x approaches z, of f of x is L. The limit, as x approaches c, is equal to L. Let's look at an example. Let's look at a line. So we did a lot of the limit stuff with end behavior. Remember that in Math 4? Like, the limit as x approaches infinity, we're going left, we're going right. Well, now we're just going to deal with specific numbers. The limit as x approaches 1 of the 2x function. I want to know what this is equal to. So let me take a look at a little picture of my good friend 2x. Oh, hi, 2x. Hi. Thanks a lot. Hi. There's 2x. You see it? Okay. Let me ask you this question. And this is going to be completely different than anything limit. I'm going to ask you for the 2x function, if f of x equals 2x, what is f of 1 equal? Yeah, what that means is, well, what's the function value when x is 1? It equals 2. And you see it right there, right? When you ask this question, when you ask the limit question, that has nothing to do with function values at all. What a limit means is, as you come from the left and as you come from the right. So I don't look here at all. I don't care what's there. Limit does not care at all what's there. What it does care about is, as you're coming up, as you go towards 1 from the left side, like you're coming from the left towards it, where's the function going? Hey. And then as you come from the right side, as you come from over here towards 1, where is this function going towards? What number is it coming towards from the left? As you get closer to 1, what y value are you getting closer to? 2. As you get closer to 1 from the right, what y value are you getting closer to? 2. And that's sort of that bucket. As you if you set up a bucket of x values, and you get closer and closer to the 1, we're going to get closer and closer to the 2. That's what that kind of bucket means, okay? But that's what a limit is. It's as you get closer and closer to the value from the left and to the right. And here's how you would write it. The limit, as x approaches 1 from the left of 2x is equal to 1, equal to 2. The little exponent negative sign means the limit as x approaches 1 from the left. Okay? And what we do is we just look from the left and it approaches 2. The limit as x approaches 1 from the right of 2x is also equal to 2 that you just told me. What this is saying is as you get closer to 1 from the right side, from the plus side, the function approaches 2. Now, if the limit from the left equals the limit from the right, the limit exists and it is equal to that number. The only time a limit exists is if the limit from the left is equal to the limit from the right, then the limit exists and it's equal to that value. Okay? Let's look at another example. And with continuous functions like this, like a line, you could just dump in. Since this is a continuous function, it's just going to equal 2. You know what I'm saying? It's like, are we seriously going to do this, Mr. Enos, all day? Are we serious about this? I am serious about this. With a continuous function, you can just dump in, but that's not always the case. Let's look at this. Let's look at this special friend. Ever take a look at in your notes, which is there, problem 10. So I want everyone to graph this thing again. You know, pretend these are all x's. I don't want that to confuse anyone. X. Graph that function, x squared plus 5x plus 6, and then x plus 2. This one right here, example 10. And I want to know what's the limit as x approaches 2. Yeah, get in there.